Okay, let's continue the discussion about singularities. We know that what is a pole? F has a pole at z equal to a. Pole means the limit z approaches a, absolute value of f of z is infinity. So it means this. So if this value of f of z is infinity, then we know the limit z approaches a 1 over f of z. Here we don't even put up value, it becomes 0. Right? It will become 0. And also here, whenever we put the ratio, the reciprocal, we have to assume here f of z is non-zero, right? F of z is not equal to 0. But it's okay, since when z approaches a, the ups value is infinity, approaches infinity. So close to a, all the ups values will be very big. So here, actually, this condition, this is also a local information. This is a local information. So f of z is not equal to 0 for z sufficiently close to a, right? When a is sufficiently close to a, f of z is naturally non-zero, and then you can form the reciprocal. All right, so this makes sense. This makes sense. Then we know what? We know z equal to a is a removable singularity of 1 over f of z. It becomes a removable singularity. Why? Remember, whenever you have a analytic function in a sufficiently small neighborhood, removable singularity means limit z approaches a z minus a times remember that analytic function with sorry, not a, z, f of z, this is 0. And here, even without multiplied by z minus a, this limit is 0. So this is a equivalent characterization. So here, we of course have z minus a, 1 over f of z. This product has limit 0 at a. This one has limit 0 at a. This one has limit 0 at a. The product has limit 0 at a. Okay, so z equal to a becomes a removable singularity of 1 over f of z in a small neighborhood, in a neighborhood of a. We're talking about a neighborhood, a small enough neighborhood. All right, so now in this neighborhood, we define h of z. We don't want to always look at 1 over f of z. We let h of z be the extension, be the analytic extension. Okay, of 1 over f of z. It just means that h of z is analytic and h a is equal to 0. In a neighborhood, in the neighborhood, this neighborhood, in the neighborhood of a, and h of a clearly should be 0. It's a limit. It is this limit. Okay, for the analytic function with a 0 at a, then we know there is an integer m such and an analytic function g of z such that h of z is equal to z minus a to mth power times g of z, and g of a is not equal to 0. Right? We have a factorization. Okay? So from here, let's check. If z is not equal to a, so for z not equal to a, z is not equal to a, 1 over fz is h, so this is h of z is equal to this product. And we flip them, we will have, we can flip them. One, z is not equal to a, so g of a is not 0. In an even smaller neighborhood, g of z is not 0. Right? That's like the continuity of the function. So we get f of z is equal to, we flip it, so it's z minus a to mth power times g of z. Here in a smaller neighborhood of a, g of z is not equal to 0. Okay, so this makes sense. It's not just for a point for a small neighborhood. So this implies f of z can be written as 1 over g of z. This is an analytic function. Since it's a reciprocal of an analytic function, so it's analytic over z minus a to mth power. All right, so here, this one, of course, is non-zero, and it is defined in a neighborhood. All right, so when you have a pole, you can always write f of z as an analytic function over z minus a to mth power. Here, this numerator, the analytic function, is non-zero. At a, is non-zero at a. Actually, in a neighborhood, it's not zero. Okay, so to summarize what we just investigate, we have the proposition 1.4. Proposition 1.4 says if G is a region with A in G, and if F is analytic on G without A with a pole at z equal to a, with a pole at z equal to a. Okay, so we have a pole, then there is a positive integer m and an analytic function g analytic function g from the region G to C such that f of z is equal to g of z over z minus a to mth power. Okay, so this is a proposition 1.4. So in this proposition, we just say there exists a positive integer with such property, and this m is not unique. From the proposition, we never mention m is unique. It's because we never require the numerator g is not zero at a. For example, you can have such thing, or you can just multiply numerator and denominator by whatever powers of z minus a. You always have it. So g and m are both non-unique in this proposition. Okay, and of course we want some uniqueness. Uniqueness means, you see here, we can multiply them by any positive power, but we cannot multiply by negative power. If we multiply by negative power, the numerator will not be analytic. So we definitely have a smallest positive integer satisfy this property. Okay, so the definition 1.6 says if f has a pole at z equal to a and m is the smallest positive integer such that such that you see here that the language is like this. So f of z times z minus a to mth power. You move this to the left side. It becomes g of z. Okay, this has a removable singularity. It has a removable singularity at z equal to a. Right? Then we say f has a pole of order m. At z equal to a. So basically, fz times z minus a to mth power is equal to g. So when this g barely exists, then this is the order of m. The order of m. Okay? All right. So in this, so this is definition. And in this part, in this definition, if m is the order of the pole a, then remember this g of z equal to f of z minus a. It has no 0 at z equal to a. At z equal to a, g of z is not equal to 0. It's because g of z actually is a reciprocal of certain analytic function. All right? So here we just emphasize g of a is non-zero. If g of a is 0, this one, we can drop this m. Right? We can drop this m. You can do the contradiction part, and the contradiction is about the smallestness. Right? Okay, so whenever you have an analytic function with a pole of order m, you always write this way. Okay, so now let's continue this investigation. Let f have a pole of order m at z equal to a. And assume we already have f of z is equal to g of z over z minus a to mth power. So g is analytic. Remember, g is analytic. G is analytic. It is analytic in an open disk. In a disk BAR, some disk. Then analytic function in the open disk must have a power series expansion. G has a power series. Expansion at z equal to a. At z equal to a, we talk about the z equal to a. So let g of z is a m minus 1 z minus a. So here we don't start from a0 because later we will see why we don't want to start a0. We just put am. This is power m, so this is m, and then you continue, you increase this. Not increase it. You just m minus 1, m minus 2, decrease it. A m minus 2, z minus a square. Until you reach what? You reach a1. A1, what is a1? A1 is a z minus a to power m minus 1. See, here's the first power m minus 1, second power m minus 2. M minus 1 power is m minus, it is m minus 1. Okay, m minus 1. We just want the first a few terms. And then if you have z minus a to mth power, z minus a to mth power, we will call it a0. a1 z minus a to power m plus 1. It's supposed to be 0, but we use a little letter, little a, not a capital A, not capital. We use a little a. And this time we're going to increase a2 z minus a to power m plus 2. So from here we start from a0, a1, a2. And the first part, we still keep them. And this part we can fact out. We can fact out. The minimum power is z minus a to m's power. So if we fact out, it's a z minus a to m's power. Then you will have a0, a1 z minus a2 z minus a squared, and so on. So this tail can be also written as z minus a to mth power and sigma k from 0 to infinity, ak z minus a to k's power. All right. So what is the g of z? So g of z is am minus 1 z minus a up to a1 z minus a to power m minus 1, and then plus this part, z minus a to power m and sigma k from 0 to infinity, ak z minus a to k's power. Right? So that's a power series expansion. We just artificially separate the first m terms, because the first m terms, the power, all the powers are less than m. Start from the m plus 1's term, the power is greater than or equal to m. Okay, and then we're going to divide each term by term by the z minus a to m's power. So we get f of z equal to g of z over z minus a to m's power. Then what we have? We will have capital am z minus a to m, capital A m minus 1. Here z minus a, denominator m, so it's a z minus a to m minus 1. You see here, that's why we want to match them. Until last one, a1 is a z minus a to first power. In this tail, we cancel z minus a to m's power, so we just have sigma k from 0 to infinity, a k z minus a to k's power. Okay, so we just want to separate the rational part from the polynomial part. Okay, and remember that we mentioned this G of A is non-zero, so this capital M, AM, capital AM is not equal to 0. Capital AM is not equal to 0. It is a G of A. This is equal to G of A. It's non-zero. So you do have the first leading term non-zero. Okay? Okay, so let's see the definition we want. This is a polynomial part, not polynomial, a power series part. This is, we'll give a name about it. So if f has a pole of order m at z equal to a, and f satisfies here, this one, this is called 1.7. This expansion is called 1.7. Satisfy 1.7. Then this part, am, z minus a to m's power, plus up to a1, z minus a, is called the singular part. The singular part of f at z equal to a. Singular part, non-defined. You do have the pole in this part. This is the analytic part. So if you want, you can call this analytic part. This is a singular part. Right? Correct? Okay, so we have a singular part for the analytic function with a pole at z with order m. Okay, so now let's put this in apply this to the example. So consider a rational function. A rational function r of z is equal to p of z over q of z. Rational function always has no unique form, right? If you want, you need numerator and denominator co-prime, right? So here, where p of z and q of z are polynomials, without common factor. Without a common factor, you cannot do cancellation. It's called the irreducible one, right? Irreducible form. If they don't have a common factor, then we know then the pole of r over z, the poles, may not have just one. The poles of r over z are exactly the zeros of q over z. So you find the zeros of q over z, they are exactly the poles of r over z. And q over z, you when you have a zero, you have a power order, and that is also the order of a pole of r over z. So the order of each pole of r over z is the order of the 0 of q of z. Okay. All right. So let's apply this singular part process. So assume q of a is 0. Q of a is 0. We have a 0, we have a pole. And let S of z be the singular part. Be the singular part of R of z at A. Okay. You have a singular part, you have a the rational function. Then R of z minus S of z. Let's call it R1 of z. And R1 of z is also a rational function. So far we only know it is a rational function. Rational function. Okay, it is a rational function, and this rational function, we know the poles of this new rational function are also the poles of R of z, but it's not the pole of A is not a pole, and A is not a pole. R1 of z. A is not a pole of R1 of z, right? Well, A is not a pole, then the poles of R1 is still the pole of R, then you continue this. Continue this process on R1 of z. R1 of z, you will have zeros, the poles, and you separate the singular part. Okay, by induction. By induction, we will have R of z equal to sigma j from 1 to n Sj of z plus p of z, where Sj of z is the singular part of Rj of z. S1 is the singular part of yes, this S, you can consider it as S0. S0 is the singular part of R. And we have to stop, so P of z has no singular part. No poles. Has no poles. P of z is a rational function. A rational function, it has no poles, so the denominator has no 0. If a denominator has no 0 in the complex number system, denominator has no 0, then the denominator is a number. It's not a polynomial. It's not a function anymore. It's just a number, constant number. So this P of z is actually a polynomial. It's actually a polynomial. And when you have a rational function, right, you go through this process, get such decomposition. This is actually what we actually did this in the calculus. This is a partial fraction. This is the partial fraction. Partial fraction, right? So how do you do the partial fraction? You actually do the long division and simplify the, so partial fraction, first is a long division, division. Okay, sorry, I don't remember how to write the division. Oh, long division, yes. You do the long division, you make sure that the degree of the numerator is strictly less than the degree of the denominator, and that is actually the sum of this, and then you have several strategies to get it, right? Okay, so that's the partial fraction. The partial fraction, if R is required to be a rational function, then this remainder, actually the remainder P of Z, must be a polynomial function. Okay, of course, if R is an analytic function, in G with finitely many poles. We want it to be a finite. We don't want to get infinite sum so far here. Then this P of Z can be an analytic function. All right, so you can just separate the singular part and you still get an analytic function. Okay. Here we need a special. We need a requirement. This the number of poles must be finite. If the number of the poles is infinite, then you need additional theory to guarantee the decomposition. So if R has infinitely many poles, then it is okay. So we have this Mittag. It is Mittag Leffler theorem. In the future, we don't have time to touch it. All right, so we do have some analog of such situation. So in the rational case, it's a long division, which is have singular part, analytic part. If we have analytic function with a finitely many poles, we can also do this process. But if we have infinitely many poles, then it is more advanced. Then there's an analog of a theorem here. So that's the discussion about the pole. Pole, you will have singular and analytic part. And what happens if we have a essential singularity? Removal is just analytic, so we don't discuss removal. So this is the second singularity. It's a pole. And if we want to discuss the similar situation for the essential singularity, we will have a framework. We need a framework to put the essential singularity in that. So we will continue that discussion in the next video. Okay? Thank you very much.